and get back up to speed, because we are going to be doing a lot more very, very interesting rational trigonometry in the months ahead. Opening up all kinds of new business, very exciting stuff, and lots of opportunity, as usual, for people to make interesting contributions and discoveries yourself. All right, so rational trigonometry is an early theory. It hasn't been around for very long. A lot of mathematicians still don't know about it, so it's a great opportunity to get on top of things and forge ahead in a brand new interesting direction. Now, let's have a closer look at this dot product that we just introduced. So this is another way of combining two vectors and getting a number. And we might call it the blue dot product because it's going to be just one of three dot products that are shortly going to figure in sort of a wonderful trilogy. This is a familiar dot product that undergraduates learn about. Here it is again. There's the dot product of the two vectors, so AC plus BT. And by the way, if you want a bit of a review of these things, you have a look at log trick 46 to 51. Okay, so there's various properties of this dot product which are important to identify. Firstly, we want to remind ourselves or observe that the dot product is linear. And what does that mean? Well, it means that if you take, say, V dot, the sum of W1 plus W2, here are two vectors being added, you take the dot product between V and the sum, then you get the sum of the dot products V dot W1 and V dot W2. And that also happens on the other side, so if we take V1 plus V2 dot W, then we get V1 dot W plus V2 dot W. And also there's a linearity with respect to scalar multiplication, that if we multiply V by some number lambda, and take the dot product, that's the same as taking lambda times the dot product of V and W, and that's also the same as V dot lambda W. So that scalar can be moved around from being in front of W to being in front of V to being in front of the dot product itself. Then three other important aspects of the dot product. First of all, the quadrants of the vector is just V dot V. The crucial metrical quantity can be expressed as a dot product of a vector by itself. So mathematically, sometimes say that's a quadratic form. Another very important property of the dot product is that it's symmetric. That V dot W equals W dot V. You change the order, the dot product does not change. And a little bit more subtle, this property of connection with perpendicularity. That two vectors are perpendicular precisely when the dot product is zero. So this is another very important feature of the dot product that will allow us to identify the two vectors are perpendicular algebraically. We just hold their dot product and make it zero, they're perpendicular, and if it's not zero, then they're not perpendicular. So we need to talk a little bit more about this perpendicular property of the dot product. Students who take linear algebra courses are often taught that perpendicularity is defined in terms of the dot product. And we just define perpendicularity by the dot product being zero. But that's not really the whole story. So we can legitimately ask, why is it that we define perpendicularity via the dot product? Or in other words, why are these two things really equivalent? And the key is to understand that perpendicularity is a classical concept that really goes back to Pythagoras. It's Pythagoras' theorem that controls perpendicularity, or allows us to identify perpendicularity, going all the way back to Euclid, of course, and earlier. Okay, so here is a picture. There's a vector V. There's a vector W. And let's consider a triangle, because Pythagoras' theorem is relating to a triangle. So let's consider this vector that's emanating from here to here. Now, in vector language, if this is V, and that's W, then this vector here is W minus V. Because it has the property that you take V, and then you add the W minus V. That combination is the same as just the single vector W. So we have a triangle here now with three sides, they're vectors, V, W, and W minus V. Okay, so what does Pythagoras' theorem say? Well, Pythagoras' theorem is saying something about the quadrances, that we should have perpendicularity there, precisely when this quadrant plus this quadrant equals the hypotenuse quadrants. So here's the statement involved in Pythagoras' theorem, that QV plus QW equals QW minus V. And let's just look at this statement and rewrite it using what we know about dot products. Okay, so this statement is equivalent to the following statement. We've just rewritten this statement here because we've replaced Q of V with V dot V, replaced Q of W with W dot W, and replaced Q of W minus V with W minus V dot W minus V. Okay, so now we have to expand this. How do we expand this? Well, we can use the linear property of the dot product, allowing us to basically use the distributive law. This is really W dot W minus W dot V minus V dot W plus V dot V. There's four terms. And if you write down those four terms, you'll see that two of them cancel with the things on the left-hand side. The V dot V, which is dot product of those two, and the W dot W, which is product of those two, they cancel. So this equation here, the second one, is equivalent to this third equation, which says that 0 equals minus W dot V, that's product of those two, minus V dot W, which is the product of those two.